Hi, this is Amanda Birch.
And this is Daniel Wieland, and the first topic we'll be talking about today is peak shapes. On an emission spectrum, the shape of the peaks is determined by the distribution of magnitudes of emission intensity over a certain set of wavelengths. Keep in mind that discrete quantized amounts of energy are necessary to excite an electron within a molecule to a higher energy state. As the electron returns back to a favorable ground state, potentially through intermediate energy states, it releases lower energy photons and emittance that are proportional to the differences in energy between these energy states. The greater the favorability of achieving a lower energy state, the greater the probability the excited electron will return to lower energy states, resulting in a greater rate of photons to be released at wavelengths that reflect the differences in these electron transitions. This corresponds to the intensity. Complexity of these energy levels is determined by molecular composition, intermolecular forces, and thermodynamics. In general, the larger the molecule or the more electron-dense the atoms, the more potential energy levels an excited electron can jump to. This also results in a greater number of ways that an electron can return back to ground state through intermediate energy levels. Bonded electrons that have achieved lower potential energy states require more energy to excite, and therefore have the ability to release higher energy, shorter wavelength photons as opposed to higher potential energy unbonded electrons. Intermolecular forces also influence the differences between energy states because they cause small distortions to energy states that an electron can jump to, resulting in a range of wavelengths at which a photon can be absorbed and emitted. Thermodynamics will be discussed later in relation to Stokes shift. When absorption and emission spectra are compared for the same substance, a mirroring effect is observed. The two spectra appear to have the same pattern of peaks and troughs. This makes sense because energy levels in a molecule are quantized. Energy is input at discrete wavelengths, and this causes excitation to specific energy levels. When the molecule releases energy, it only can release to discrete energy levels. Because these energy levels do not change significantly over time, the wavelengths absorbed are very similar to the wavelengths emitted. This is assuming that the same energy level transitions are passed through in absorbance and emission. Of course, the wavelengths of photons emitted will be significantly different when one photon is absorbed and three photons of very long wavelengths are emitted. This results in mirrored spectra, where both the absorption and emission graphs appear to have the same shape. However, the spectra do not necessarily have to be exactly mirrored. On the green absorbance spectra, the peak appears to have two tips. However, on the emission spectra, this is smoothed into one peak. This can be explained with Stokes shift, which can be different for different energy level transitions the excited electrons may take. The mirrored peaks should still look similar for the same substance.
However, the two are not exactly identical. A redshift in the emission wavelengths is extremely common. This phenomenon, known as Stokes shift, is due to thermodynamics. In the excitation process, a tiny amount of energy is lost to heat, and the atom actually relaxes minutely into a state of excitation slightly less than that which would be achieved by the entire input of energy. When the atom relaxes to a lower energy level or to the ground state, slightly less energy is emitted than is absorbed, because not all of the absorbed energy excited the electron. This shift cannot occur in the opposite direction, because an electron cannot emit more energy than it absorbs. It is energetically unfavorable for the electron to be in a state closer to the nucleus than the ground state, and so the ground state represents the minimum energy state of the electron. The maximum amount of energy that can be emitted is the difference in energy between the excited state and the ground state. This can never be more than the amount of energy absorbed during excitation, but will be slightly less due to the loss of some energy. These concepts can be modeled by thinking about rock climbing. When the rock climber moves upward, he is exerting energy to reach a state of higher gravitational energy. The energy he expends to climb the rock is analogous to the absorbed energy in an electron, and the gravitational energy at the top is analogous to the energy at the highest energy level. However, the gravitational energy at the height he reaches is slightly less than the energy he expended to get there, because he lost some energy in the form of heat. He is hot and sweaty after this energetic jump. When he jumps back down, the gravitational energy he gained through climbing is transformed into kinetic energy. However, the total of this kinetic energy is still a smaller quantity than the energy he put in to reach this height. He cannot regain that energy lost through heat. Likewise, the energy emitted from a substance to return to the ground state is less than the amount of energy absorbed to excite the substance, because some energy takes the form of heat. This energy is emitted in the form of infrared radiation instead of visible light, and therefore cannot be seen in our emission data.
And those are the major influences on available energy level, peak shape, and the differences between absorption and emission spectra. Thanks for watching.